During 2020, GeoSolutions has participated to OGC Testbed 16, implementing a DGGS server component. Discrete global grid systems have the potential to enable storage, analysis, and visualization of geospatial information in a way that more accurately reflects the relationship between data and the Earth. However, effort is needed to concretely demonstrate DGGSs and drive their adoption. GeoSolutions used GeoServer to support the Testbed 16 goals. New modules have been developed using the RealPix and H3 libraries, as well as the ClickHouse database. DGGSs have been exposed via traditional OGC services, via a dedicated DGGS API, as well as a DAPA API. Overall, these implementations support the visualization, download, navigation, and analysis on top of DGGS data. In accordance to the testbed requirements, all code changes have been made open source as GeoServer community modules under the OGC API implementation subsystem. Before delving into APIs, let's have a quick look at DGGS concepts. A discrete global grid system is a partitioning of the Earth into equal area zones. This partitioning, unlike equal area projections, has no arbitrary limits, such as the dateline or the poles. The partitioning is hierarchical, wrapping the planet with zones at multiple resolutions, and zones share parent-child relationships as well as neighborhood relationships. A DGGS library provides the mathematical implementation of the partitioning and allows to answer questions such as converting between zone identifiers and their boundaries, converting between points and polygons and their corresponding zones, navigation between parent, children, and neighboring zones. The Testbed 16 server has been implemented on top of two libraries, one for the RealPix DGGS and one for the H3 DGGS. The RealPix DGGS is based on equal area zones. Each zone is subdivided into 9 children, and each has 4 neighbors. The zone identifiers are easy to reason with. For example, P is the parent of P1 and P1 is the parent of P12. Currently, only a Python 3 library implementation is available. H3 by Uber is based mostly on hexagons, each one having 7 children. Occasionally, a pentagon is found too, which has 6 children. The system is designed for efficient navigation, with each cell having 6 neighbors at the same distance. However, zones are not exactly equal in area. Zone identifiers are hexadecimal representations of a 64-bit number and are hard to reason with. H3 has a range of library implementations covering a rich set of languages including C, JavaScript, Java, Python, and more. The first step in the server implementation has been visualizing DGGSs. In order to do that, a purely geometric DGGS data store has been implemented in GeoServer, communicating to the libraries through a common interface. The store can be configured like any other store and can be used as a data source for WMS or WFS services. Integrating the RealPix Python library in the GeoServer Java runtime proved difficult. The JEP project has been used to bridge the gap. However, lack of support for multi-threading in Python means performance and scalability are limited. Here is a WMS representation of the RealPix DGGS using a plot carrée projection at resolution levels 0 and 1. And here is a corresponding representation of H3. Visualizing the structure via WMS helps a lot understanding DGGS geometric structures, as well as viewing parent-child relationships and neighborhood ones. DGGS zone boundary and attributes can also be downloaded via WFS to be then displayed with a separate tool, such as QGIS. With a better understanding of DGGS structures, we moved on to representing data on top of the DGGS grid. The number of zones covering the planet can grow very large, up to hundreds of trillions at the maximum resolution. This can be challenging for a classic relational database. Also, DGGS structures are particularly interesting for data analysis. Based on that, the ClickHouse OLAP database has been chosen for the prototype. While ClickHouse retains a familiar SQL access, tables are partitioned by default and can be spread over multiple nodes. Thanks to partitioning, queries can run using all available CPUs, speeding up data retrieval and analysis. For the test, we used Sentinel-2 images and sampled them at resolution 11 on both RealPix and H3, covering all 13 bands available. The Australian Capital Territory has been used as the area of interest. In addition to the 13 bands, the normalized different vegetation, water, and built-up indexes have been computed. Once resolution 11 has been populated, lower resolutions have been calculated via fast parent-child aggregation, resulting in a multi-resolution representation of the dataset, available in ClickHouse for querying. A GeoServer data store has been built on top of it, and making this multi-level hierarchy available for WMS and WFS usage. While classic OGC services can be used to explore data, a dedicated API can take advantage of the unique nature of DGGS, both in terms of extra semantics and performance. The group designed a DGGS API reminiscent of OGC API features. In particular, data is still organized in collections. However, the API comes with some unique additional abilities. For example, access to zones requires usage of the target resolution. Also, space filtering can be performed via a few different flavors. By a CRS-84 bounding box, just like in OGC API features, by a CRS-84 polygon, and finally, by a list of parent zone identifiers. The latter is at the same time native to DGGS and the most efficient in terms of data retrieval. A dedicated resource allows to retrieve neighbors of a given cell up to a certain search radius expressed in number of cells. Here are the results of searching with a radius of 2 cells in both RealPix and H3. Other dedicated endpoints allow to discover parent and children up and down to a target resolution. Here are the results of getting children that are 2 levels down compared to their parent. Finally, 2 resources are available to map real-world geometries onto DGGS zones. The first one is given a point and a target resolution, returning the DGGS zone covering the point. The second one is given a polygon and a target resolution, returning the set of DGGS zones covering the polygon. Optionally, the returned set can be compressed by returning parent zones when they fully fit inside the polygon. To wrap up, let's consider data analysis. The Data Access and Processing API has been developed during Testbed 16 to provide analytics extensions based on collections. In particular, it provides aggregations over position, area, and time ranges, eventually both. The DGGS flavor of the API allows to aggregate zones with a choice of target resolution and a possibility to specify the area of interest as a set of zone identifiers. Aggregations are pushed down to ClickHouse for best aggregation performance. As an example, we computed min, max, and count aggregates over the entire area of interest and over all 16 attributes. The request has aggregated 9 million records in less than a second, despite having no indexes on the attribute columns. The resolution parameter allows to control the trade-off between speed and accuracy. Analytics users, such as Jupyter Notebooks, can use low resolution for development and switch up to higher resolutions to get the final results. Thanks for watching. If you'd like to get more details about this activity, please look up and read the OGC Testbed 16 DGGS and DGGS API engineering report, as well as the OGC Testbed 16 Data Access and Processing engineering report on the OGC website.